This is the second video in Chapter 18 dealing with standing wave and resonance. Standing waves in air columns. To have a standing wave in an air column, the open end of the air column has to be an antinode. If you have an air column, the open end is where the air can move in a maximum type of amplitude because it's free to move in any direction. Whereas the closed end has to be the node, because the closed end, the air can't move obviously at that point where it's closed. So we have these constraints: antinode at the open end, node at the closed end. As with standing waves on a string, there's half a wavelength between successive nodes, and for that matter, half a wavelength between successive antinodes. So it's exactly the same rules between the nodes and the antinodes. Also, a node-antinode pair will again be a quarter wavelength apart. So here's an example. Here we have an open-end pipe, and we're just showing the cross-section here, so we have it sliced open from the side so you can see it. And we have, at the open ends, we are constrained to have antinodes, maxima. So for our simplest standing wave that we can possibly have, we have an antinode at one end, a node in the middle, and an antinode at the other. That's the simplest standing wave we can get. And we know that between two antinodes, there should be a half wavelength. So the length of this tube is indeed, in its simplest configuration, a half wavelength long. The frequency that corresponds to this would be the velocity of sound divided by that wavelength, the wavelength being 2L. So the fundamental frequency of this open-end pipe is the velocity of sound divided by 2L. If I want to get another standing wave, another harmonic, I am again constrained to have an antinode at either open end, but I can also add another antinode-node pair in between. So now the length of this tube is half a wavelength plus half a wavelength, or one full wavelength. The frequency that corresponds to that is the velocity of sound divided by the total length, L. Again, if I want the next point of resonance, antinodes at either end, add another antinode-node pair in between. So now I have half a wavelength, half a wavelength, half a wavelength. Total length is 3/2 wavelengths. This frequency is the velocity of sound divided by that wavelength, 3/2 velocity divided by L. So we can see that our fundamental is the velocity of sound divided by 2L. The second harmonic is twice that, and the third harmonic is 3 times that of the fundamental. So for a pipe open at both ends, our natural frequencies of vibration form a harmonic series, and they're given by the nth harmonic is equal to n, an integer 1, 2, 3, 4, and so forth, times the velocity of sound, which we generally take to be 343 meters per second, divided by 2 times the length of that open-end pipe. What happens if we had a pipe that was open at one end but closed at the other? In this case, we are constrained to have a node at one end and an antinode at the other. And in our simplest configuration, we have a standing wave where we have a node and an antinode. They must be a quarter of a wavelength apart, so the length in the simplest configuration is 1/4 wavelength. The frequency that corresponds to that would be the velocity of sound divided by the wavelength, which is 4L, velocity of sound divided by 4L. The next harmonic possible will still have a node at one end and an antinode at the open end, and we'll have an antinode-node pair added in between. So the length is going to be half a wavelength plus a quarter wavelength, 3/4 wavelengths, and this frequency will correspond to 3/4 velocity of sound divided by L, 3 times the fundamental. So it's actually the third harmonic. We lost the second harmonic. The next possible standing wave, node at the closed end, antinode at the open end, another antinode-node pair added in between. Length is equal to 5/4 wavelengths, and the frequency is 5/4 velocity of sound divided by L. So for a closed-in, open-end pipe, only our odd harmonics are present. The even harmonics disappear. And the natural frequencies are n times the velocity of sound divided by 4L, where n is a odd integer, 1, 3, 5, 7, 9, and so forth. Mathematically, we could express this a little bit better, at least in terms of a mathematician might think, as 2n minus 1 velocity divided by 4L, where n is 1, 2, 3, 4, and so forth. But I think n velocity over 4L, and just recall that n must be an odd integer. I think that's easy to remember. So let's try this out. Calculate the length of a pipe that has a fundamental frequency of 240 Hertz if the pipe is open at both ends and closed at one end. Well, the wavelength we're thinking about is the velocity of sound, 343 meters per second, divided by this frequency, 240 Hertz. So the wavelength of the sound we're looking for is 1.43 meters. To produce that in an open-end pipe, at least at the fundamental, we need the length of the pipe to be half a wavelength. So that will be 1.43 divided by 2, or 0.715 meters. We could also do it with a closed-end, open-end pipe. The length then would be 1/4 of a wavelength, 0.357 meters. That'll produce the same sound, maybe not quite as pure. So if we were devising a pipe organ to be used in the Mormon Tabernacle Church, we might want to consider how much space we have. If we have unlimited space, we'll just make all the pipes open-end, open-end, and not worry about it. But if we're confined, then we might have to design some of our pipes to be closed-end, open-end, so that we can fit them in there and produce the same sound. Let's try this problem. A tuning fork of frequency 512 Hertz is placed near the top of a tube shown in this figure. The water level is lowered so that the length L slowly increases from an initial value of 20 centimeters. Determine the next two values of L that correspond to resonant modes. Well, if we have 512 Hertz, our frequency should be equal to n times the velocity of sound over 4L for a closed-end, open-end pipe. So our possible locations are going to be a quarter wavelength, 3/4 wavelengths, 5/4 wavelengths. These will be our locations that will correspond to resonant standing waves. We're going to arrange this equation for our frequencies to get the lengths that we need equal to n, where n is an odd integer, velocity of sound over 4 times the frequency. Frequency is already determined to be 512 Hertz. So only our odd harmonics are present. So for our n equal 1, we would have 343 divided by 4 times 512, or 0.167. And in general, our odd harmonic will be that value for n equal 1, 0.167 times n. So our first one will correspond at 0.167 meters, or 16.7 centimeters down. Well, we've already missed that point because the water level is already at 20 centimeters down. So we missed the first position of resonance. So we have to look for the next one. That's the third harmonic at 3 times this distance. 3 times 0.167 is 0.502. If we were to lower the water down to 0.502, we would hear a louder sound of the standing wave and hit resonance at that point. And the next one will be the fifth harmonic at 5 times the fundamental, 0.837 meters. We lower the water down to that point, we'll hear another maxima at that point. Beats. Consider two waves of equal amplitude, but with slightly different angular frequencies, omega 1 and omega 2. If we were to add these two waves together, a naught sine or cosine omega 1t plus a naught cosine omega 2t, and we're going to use the trig identity, cosine A plus cosine B equals 2 cosine A minus B over 2 times cosine A plus B over 2. Combining these two waves, we get that our combined wave function is 2a naught cosine omega 1 minus omega 2 divided by 2 times t cosine omega 1 plus omega 2 divided by 2 times t. This is a superposition of these two waves at two frequencies that are close, but maybe not exactly the same. Now we can see that a term where these two are really close, not exactly the same, but if we add them together and take their average, that pretty much would be the average frequency, which is very close to either frequency, omega 1 and omega 2. So that part of it will just be a nice angular same frequency as before. But over here we have an amplitude that depends on the difference of the frequencies divided by 2, the angular frequencies divided by 2. And the amplitude can go as high as twice the amplitude of the interfering waves. So we'll have a maxima of either positive 2a naught or negative 2a naught every period. So the actual frequency of these beats where we hit these maxima will be 2 of those every cycle, because we're going to hit a maxima at positive 2a naught and a maxima at negative 2a naught. So the frequency of the beats would be twice the frequency of the frequency within this cosine function. So we'll have 2 times omega 1 minus omega 2 divided by 2. The 2's cancel. And our beat angular frequency will be the difference between the two angular frequencies of the interfering waves. And we don't know which one is larger than the other, so we'll take the absolute value between this difference. So for the frequency, the beat frequency, we divide it by 2 pi, and we get the same thing. The beat frequency will be the difference between the two frequencies of our two interfering waves. Absolute value. So it might look something like this. We got two waves interfering with each other. At first they might constructively interfere, giving us a maxima, but they slightly start going out of phase over time, and at some point they're going to be totally out of phase, one going down while the other one's going up, so they cancel out. At that point we get a beat. So we'll go alternating between a maxima of 2a naught down to a beat or node of 0, and then going eventually back into phase where we go back to 2a naught again. And hence we see successfully at different times these beats which correspond to the nodes where we have total destructive interference. The time between these beats, these nodes, is our beat period. 1 over that will be our beat frequency. You can measure this beat frequency, or this period, go 1 over it, and that should be equal to the difference between your interfering frequencies. You could do this also with a natural system that you force a frequency onto it, and if you start observing beats, then you know that your forced oscillation is very close in frequency to the natural frequency, and by measuring the beat frequency, you would be able to determine where the natural frequency was. Because you know that the difference of your forced oscillation, either positive or negative from the beat frequency, rearranging this equation up here, will give you your natural frequency. So one of those will work. So once you measure the beat frequency, either add that to your forced frequency or subtract it from your forced frequency and see what happens. One of those is going to end up in resonance, and you'll start seeing the system oscillate out of control. Let's try this out. While attempting to tune a C note on a piano at 523 Hertz, the piano tuner hears 2 beats per second between the oscillator and the string. A lot of times the tuner will have a definite oscillator at a definite frequency, and they'll pluck the string, and then they'll listen for the beats, and then use that beat frequency to help determine how much tighter or looser they have to adjust the piano string. What are the possible frequencies of the string? The beat frequency tells that the piano is 2 Hertz off of the oscillator frequency. So our possible frequencies are 523 plus or minus 2 hertz. When she tightens the string slightly, she hears 3 beats per second. What is the frequency of the string now? By tightening the string, we realize that she is increasing the tension and that the frequency should go up. So, since we hear a beat frequency of 3 hertz, 3 beats per second, the true frequency should be above the oscillator frequency. So we have a frequency of 3 plus 523, or 526 hertz. Here's another problem. A student holds a tuning fork oscillating at 256 hertz. He walks toward a wall at a constant speed of 1.33 meters per second. What beat frequency does he observe between the tuning fork and its echo? Well, we need to use the Doppler equation for this. In this case, the velocity of the source is toward the wall. The student has the tuning fork, and he's moving towards the wall, so he's moving in the direction of what he might consider the observer. He is the observer itself, and the signal is bouncing off the wall, coming back towards him or her, and the signal is coming from that direction, and he or she is moving, or it's he, moving towards that signal. So, as the source, he's moving towards the observer. So in our Doppler equation, the observed frequency will be equal to the actual frequency, velocity of sound, and we're going to use the plus sign for the observer moving toward the wall, and we're going to use the minus sign in the denominator for the source moving toward the observer. So we're going to have 343 plus 1.3 over 343 minus 1.3, and that gives us 258 hertz for the reflected frequency. If this is compared with the actual frequency of the tuning fork, he will hear a beat frequency that's equal to the difference between those two frequencies. 258 minus 256, he will hear like that, 2 hertz. Any periodic wave function can be represented as a series of sine and cosine terms. This is called a Fourier series. Looks something like this. Our wave function y of t is equal to a summation over n of amplitudes, a sub n, sine and angular frequencies, omega sub n, t, plus the same type of terms in the cosine form. So amplitudes, b sub n, cosine, omega n times t. If the oscillation is periodic, we can put it in this kind of form with sine and cosine terms, varying the amplitudes of all the harmonics. So a sub n and b sub n are amplitudes of the series terms, omega sub n are the harmonics. And each harmonic, omega sub n, is equal to an integer multiple of the fundamental frequency. This is really neat. Here's some examples. Let's say you had a tuning fork, which is a nice pure frequency. So you have your fundamental frequency of the tuning fork. That's all you have, just the amplitude times that fundamental. In a tuning fork, there are no harmonics. So you get a pure sound at that frequency, at that note. Well, let's say you have the flute, which is a very pleasant sound, but the flute has its own unique tone to it. Even though it's playing that same note, it's got the same frequency for the fundamental, but a different amplitude, and it's got different harmonics of that fundamental frequency, giving it the characteristic tone that you associate with the flute. It's a periodic waveform with the same note, but a sound that is unique to that instrument. For a clarinet, even more complicated, with more harmonics and different amplitudes of each harmonic, giving it the characteristic sound that you associate with the clarinet for playing that note. So this is the Fourier series. All these are integral multiples, and you can recreate any periodic form of wave of this form with these series of cosine and sine terms. That concludes the second video of Chapter 18, dealing with standing waves and resonance and harmonics.